We've got a lot to cover today, so we got to go quickly. Announcements for today. Experiment 3, I warned you about this one last week too. There's a lot to do in experiment 3, so hence the reason that we need to go fast because I have a lot to tell you about. Make sure you read it very carefully before you come to lab. Know what you are doing and know not just what you're doing, but what's coming next, so you can start anticipating things and getting things ready for the next step as you're waiting for stirring or refluxing or things like that. Quiz number 3 this week, make sure you bring your calculator for the quiz, but always bring your calculator to the lab. So make sure you've always got that with you. Report for experiment 1 is due this week in lab, so make sure you've got that ready to go and ready to leave your notebook with us when you leave lab this week. Next week we'll be doing experiment 4. And your experiment 2 worksheets, so the worksheets from the modeling and modeling experiment last week are due, along with a couple of printouts that you had to print of molecules. There is no open lab next Wednesday, so the 24th of September, there is no open lab, so plan accordingly for that too. Due to CIS, Critical Issue Symposium, all classes are out of session that day, so then there is no open lab either. And then in 2 weeks, so experiment 3 is only a 1-week experiment, it's not a 2-week experiment. So in 2 weeks, your experiment 3 report is going to be due. So just make sure to prepare ahead for that, okay? So this week, in experiment 3, we'll start off the lab with making things smell like Thanksgiving and Christmas because we're gonna start with nutmeg. And you are going to extract trimeristin out of it. And then you are going to convert your trimeristin to myristic acid. Okay, so just 2 basic things here, extraction and then a reaction to get to the myristic acid. There's just a lot of pieces to get to the end, okay? So to look at the structure of trimeristin, it's very similar to other types of triesters of fatty acids. Your chain length, so we have a methyl group here, then we have 12 CH2s in the middle, and then we have our ester group here on the end. And it's a triester, so there's 3 of these linked together. Okay, so here's our trimeristin. We're going to, first of all, be taking advantage of its solubility, okay? So it's a mostly non-polar molecule. So it's very soluble in solvents with low polarity. And so the solvent we're going to be using is diethyl ether, and we'll talk about that here in a little bit. But diethyl ether is a relatively non-polar solvent, so it will work really well for this. It is not very soluble in high polarity solvents, and so specifically in methanol, or even other alcohols, but we're going to use methanol. Because methanol is very polar. Okay, so the first couple steps of the reaction, we're going to, first of all, extract, get it dissolved into the diethyl ether. The second part, we're going to, once we remove some of the ether, then get it to precipitate out with methanol. So we'll take advantage of these 2 things to get our trimeristin. Now, this triester is called a homotriester because all of the chains are the same. It's made up of the same 3 esters. And it's a triester of glycerol, okay? And most fats are triester of glycerol. Going to be extracting this fat out of the nutmeg. So the nutmeg itself looks like doesn't contain fat. It actually does, and it's about 20% or so of nutmeg is trimyristin. So kind of keep that number in the back of your mind, because we'll eventually need to calculate an extraction yield. So this is our ballpark of about how much should be coming from the nutmeg. Now to help you out, we've got your pre-lab for this week, because there is so many pieces to it, and it is slightly different than experiment 1. Your pre-lab for this week is on page 3.8 and 3.9 in your lab manual. Okay? And so it follows the same setup that we had for you in Erlenmeyer. You'll have the title of your experiment, the purpose, the balanced equations for reactions that take part. In experiment 1, there isn't any reaction that takes part. You're just doing an extraction, but you're not actually doing a reaction. So then it shows the reactions for part 2 of the experiment. You've got your physical data table, and this is based off of what you are supposed to be using, so you'll fill this out accordingly. And then you have your flow diagram, and there's 2 different flow diagrams, one for part 1, one for part 2. So make sure you pay attention to those guys and how they are the same and different than experiment 1. Same with the other parts of the pre-lab. Then for drawing of special equipment, they don't give you those, okay? So I'll tell you right now the things that you're going to need. You're going to need a reflux apparatus. We'll get to that in a little bit, what that's going to look like. You're going to need gravity filtration, if you haven't already shown that in your notebook. And then the other equipment you use is simple distillation, but you've already drawn that, so you don't have to draw that again. And for the extraction, you're just going to be stirring in an Erlenmeyer flask, so you'll be good. You've done that before as well. Okay. Then make sure for the references, make sure you change the date of the lab manual. It's the 2014-2015 lab manual. And then make sure you show the calculation of limiting reagent and theoretical yield, and make sure you understand this calculation. Okay? It's really important for writing up your report and doing the calculations for your experiment that you understand this calculation. And we're going to not go through this specific calculation, but go through the information that you need in order to understand this. Okay? So make sure when you're putting things in your pre-lab that you understand those things. Okay? All right. And we'll come back to, in a little bit here, we'll look at those flow diagrams in a little more detail. So, like I've already said, this is a really busy week in lab. Each of these pieces take a little bit of time to get to the point where you isolate your trimyristin and then isolate your actual myristic acid. Okay? So make sure that you are staying on top of what you need to be doing, as well as anticipating what the next thing is that you're going to need to do. Okay? Now, in using nutmeg in experiment 3, that's an example of, and then extracting the trimyristin is an example of isolating a natural product from a plant or animal material. So if you guys remember seminar a few weeks ago, our very first seminar speaker was talking about natural products and how natural products are used. This is a really good example of isolating a natural product. Okay? Now usually when you isolate a natural product, you're going to, a lot of times it's isolated to then look at its properties as far as being used as a pharmaceutical or being used to make a pharmaceutical, which we're not going to do. we're just going to isolate the trimeristin to then go on and do another reaction with it, okay? Usually your natural products are going to come from plant or animal material. So in this case, we're getting it from a plant. Now, what we're going to use to isolate our trimeristin and so you also this week want to practice, we've thrown in some kind of tongue twister vocabulary, so practice saying trimeristin and myristic acid and also spelling both of them. We're going to use what's called a solid liquid extraction. And so we've already used a liquid extraction. We used that the first week of lab. Now we're going to have the solid be the nutmeg. The liquid we're going to use, like I said, is the diethyl ether. And so you're going to extract the trimeristin from the nutmeg into the ether, all right? What we're going to do to then isolate our solid versus our liquid is we'll use gravity filtration. Okay. Instead of separating in this subfunnel like we did the first week, we need gravity filtration to separate our liquid from solid. And so some of you may have used gravity filtration in the first experiment if you had to do a hot filtration. So we're going to need something called fluted filter paper. So we're going to take filter paper and put pleats in it, okay? And then you will filter just by gravity, not connected to a vacuum, just by gravity, filter. The nutmeg will stay in the filter paper, and the trimeristin and ether should then filter out into your collecting flask. Couple things we have to be really careful of, though, is trimeristin is very soluble in ether, but ether is very volatile, and so you can get a lot of trimeristin into the ether, but because it's very volatile, if it evaporates, then you're going to have solid trimeristin instead of trimeristin dissolved in your ether, okay? And so you'll lose some of your trimeristin if you don't keep it dissolved in your ether. So when you are extracting, you're going to keep your funnel covered with saran wrap, and there's saran wrap in plastic wrap in both labs, okay? So keep your funnel during filtration completely covered with plastic wrap. When you are stirring your nutmeg in your Erlenmeyer flask before you actually go to filter it, keep that covered with plastic wrap as well, okay? So you want to make sure you don't lose your ether. You're trying to prevent it from evaporating on you, so you got to keep everything covered because ether evaporates really quickly. Okay. The other thing is when you're doing the extraction, just the stirring and doing the filtering, make sure you keep things clamped too so things don't fall over in your hood as you're doing things. All right? So in using the diethyl ether, the other thing is we have to be careful of some of the properties of the ether. So when we talk about diethyl ether, it can be referred to as many things, okay? So diethyl ether is also the same as ethyl ether. It's also the same as ether, if you're talking not in general about the functional group, but if you're saying you're going to use ether, that usually means you're using diethyl ether. Or you can show it symbolically as ET subscript to O. Okay, so all of these are the same thing. Now it is very volatile, so it evaporates very easily. It's also, because it is so volatile, it is very flammable. So you have to be really careful not to use it near a heat source because it'll ignite very quickly. Okay. So make sure that when you are stirring your nutmeg in your Erlenmeyer flask, make sure it's just the stirring that's on, not the heat that's on, okay? Because you don't want your hot plate getting hot when you've got these ether vapors around. And then like I was saying, make sure you cover things with saran wrap. Cover your flask when you're stirring, cover your funnel and filter paper when you're filtering, okay? But be really careful about its flammability as well, okay? You're going to extract at least 2 times with ether. And the instructions for that are in your lab manual, okay? And we'll talk about here in a minute why we do it twice instead of once. After that second extraction, you want to look at the nutmeg that you have after you've filtered after that second extraction. Nutmeg is kind of a reddish orange color. The trimeristin is an off-white color. So look at the actual what you filtered off. Look at that solid. If you see a lot of off-white in that solid, then you haven't gotten all your trimeristin out of your nutmeg, okay? So what you may want to do, there's a couple things we could do. If it looks like we could just rinse some more ether through it, we can do that and try and get the trimeristin out of the nutmeg. Or if there's a lot in there, we may have you do a third extraction. So stir it in nutmeg a third time and then filter it a third time, okay? And usually filtering it a third time, you probably want new filter paper too, okay? So after you've extracted twice, look at that filter paper, look at your nutmeg, look at the sides of the flask, see if you have any, look at the nutmeg that's still in your Erlenmeyer flask, see if it looks like you have a lot of trimeristin. If you have questions, ask your TA or your lab prof so you make sure you need a good yield of trimeristin to be able to go on and use it to make the myristic acid. Okay, so you got to be really careful to get all of your trimeristin out. Okay. So when we're looking at an extraction, and this is, we're talking about a solid liquid extraction, but a lot of these, a lot of this can be carried on to a liquid extraction as well. The extraction is going to depend on quite a few things and how successful it is. So first of all, you want really good solubility of what you're trying to extract out. And so the trimeristin is very soluble in the ether. You want good solubility, okay? The number of times you extract is also important. So that's why more extractions is better than less. So that's why we're doing 2 times 30 milliliter extractions instead of one big 60 milliliter extraction. You'll get more out doing it multiple times than just doing it once with one large extraction. Okay? And it's not just based on solubility, but it's also the more times you do it, you just are able to get more out of it, okay? You want good contact with what you're trying to extract. So like when we did the liquid-liquid extraction, we had the liquids in the separatory funnel. You shook the separatory funnel to get good contact between the 2 liquids, okay? In this case, we're going to use powdered nutmeg. That would be better than just using the actual nutmeg nut, okay? So having it all ground up is going to give you better contact than one big solid mass trying to extract it. The other thing is good stirring. So you want really good stirring, or in the case of the liquid-liquid extraction, we shook the separatory funnel well. And like I was saying, clamp your flask to your ring stand so it doesn't walk off your stir plate. And then once you're done with your multiple extractions, you're actually going to combine the extracts, okay? You're not going to keep them separate once you are done with the extraction. You'll combine everything. And then what you're going to be looking at is what is called a concentration of those extracts. And so what that is a partial, so we did a simple distillation 2 weeks ago. We're going to use simple distillation again, but we're going to use a partial simple distillation. So you're going to distill down to about 15 milliliters. Okay. And you're going to use your 250 milliliter round bottom flask for the distillation and a hot water bath, not a heating mantle, hot water bath for the distillation. In the labs, we have 250 milliliter round bottom flasks with 15 milliliters of water in them. So you can hold up your flask before you start this distillation and mark on there about where that 15 milliliter mark is. So then you have an idea when you're doing the distillation how far to take it down. Okay? And the reason for this is we've got really good solubility of the trimeristin, but you also have solubility of other stuff you don't want. So other things from the nutmeg will extract in there besides just the trimeristin. And they are soluble in the ether. So if we keep a little bit of ether in there, we'll keep the other stuff soluble in the filtrate when you're done, and we'll use the methanol to precipitate out the ether. Okay? So that's why we need about 15 milliliters of ether left after that distillation. Okay? So a couple other notes. Once we are done here with our extraction, the waste, nutmeg, and filter paper go in a container that say nutmeg waste in the hoods. So look for a big tub that says nutmeg waste on it. You want your filter paper and your nutmeg in there. What I do is let things dry out at the back of your hood until the end of the lab period. And then you can put the nutmeg, the dried out nutmeg, and the filter paper in those waste containers, okay? Don't put any water, any solvent, anything like that in these waste containers. We're trying to dry out the nutmeg and the filter paper so we can throw things away, because once the ether is gone, it's no different than nutmeg you would be using to cook with. So it can go in the garbage. We just need to get the ether solvent off. So in this waste container, do not put any water or any solvent to transfer things into the waste container. Just put dry nutmeg and filter paper with nutmeg in there, okay? And then once you've scraped things out of your glassware, if you have a little nutmeg residue, that's not a big deal to wash it in the sink. It's no different than when you're cooking and have a little bit of nutmeg residue, okay? So just be really careful with the waste and not to add, no liquids to go into the waste. Okay, so then we've got our kind of concentrate, our ether concentrate that has our trimeristin in it. We need to precipitate our trimeristin and so we'll do that using methanol, okay? So after your simple distillation, you're going to add methanol, and you should start seeing solid form, okay? If you add methanol, you've distilled off the ether that you're supposed to, and you add methanol and you don't see solid, then we've got a problem. That means we're having trouble getting our trimeristin out, okay? And so if you add the methanol, don't see solid, try sometimes. It takes a little bit for it to precipitate, so sometimes if you put it in a cold water bath, not ice bath, but just cold water bath, and swirl it around, swirl the flask in the cold water bath, see if that helps to get the solid to precipitate out. If you're still not getting any solid, talk to your lab prof and see what you need to do, okay? But at this point, especially once you've swirled it in a cold water bath, you should definitely get solid, okay? Then you're going to use vacuum filtration to isolate it. And so make sure you've got good seal on the vacuum to make sure your solid doesn't run through. You want to collect as much of this solid as possible, okay? And what you want at least 1 gram to go on, okay? So we're going to even hang on to a little bit of this in a minute. I'll explain why. But you want to go on to making your myristic acid with at least 1 gram of trimeristin. So if you don't have that after that filtration, make sure you talk to your lab prof about that, okay? But what we need to do is we've got to figure out how to do calculations with this trimeristin, okay? We have solvent wet trimeristin that we need to take on to another reaction, and we need to know how much of it is just trimeristin, not trimeristin and methanol and ether, okay? And you're going to have ether remaining, add the methanol, so it's going to be this mixture of methanol and ether. One more thing here with this vacuum filtration, you're going to rinse your solid with a 1 to 3 ether to methanol rinse, okay? And this is in your lab manual. So we need to have a way to figure out how much solid we have that doesn't include all this solvent, okay? And the ether go away pretty quickly, but the methanol will hang on. So this is what we're going to do. You're going to first weigh all of your wet trimeristin. So know how much total wet trimeristin you have. Okay, so you want a little over 1 gram at this point. Then you're going to weigh a clean, dry beaker. An empty beaker, too. And it can be a small guy, okay? So like your 30 milliliter, 50 milliliter beaker, okay? You're going to then weigh 0.1 to 0.2 grams of the trimeristin into this beaker. So if you're close to only having 1 gram, aim for the 0.1 grams. If you're definitely have more than the gram, if you get somewhere in 0.1 to 0.2 grams, you're good, okay? But if you're running low on trimeristin, aim for the low end of what you're going to say, okay? So you're going to weigh this trimeristin into the beaker, and then you're going to store it in your drawer, okay? We're going to let this solid dry, okay? So the solid will dry, and then you're going to weigh it again. And it's not like, you may be able to check it at the end of the lab period, but most likely your weigh again is going to happen in an open lab, okay? So make sure you know how much is in there of wet trimeristin, so when you come back to weigh it again, you can figure out how much dry is in there, okay? Then what we're going to do is calculate the percent mass that was actual dry trimeristin. So if we take our dry mass of our small sample and divide it by our wet mass, so what it was when you first weighed it, and multiply it by 100, then you'll have the percent mass that is dry trimeristin. So we're getting a percentage, okay? Then we're going to use this, so we're going to use that percent, and you're going to calculate how much of your, how much trimeristin you actually got from the extraction. Okay, so you know the wet mass of what was extracted. You'll take this percentage times that wet mass and you'll figure out how much of it was dry. Okay, so then you'll have a dry mass and you can calculate an extraction yield. Okay, take your weight of trimyristin divided by how much nutmeg you used in the very beginning times 100%. You'll have your extraction yield. Okay, percentage yield. Okay, then when we did this, we then go on to our next reaction. After we set aside our 0.1 to 0.2 grams, then we went on with our trimyristin into the next reaction, what we had left. So our 1 gram or more, we went on to making the myristic acid. We also need to know how much we use for making the myristic acid. So you use this percent to calculate how much trimyristin is used in part 2. And part 2 is the formation of the myristic acid. And you need to know this because you need to know you're going to have to calculate a theoretical yield for that reaction. So even though you have it in your pre-lab, you're going to calculate this number now with the actual amounts that you used in the lab. So theoretical yield and percent yield of myristic acid. Okay. So we need to calculate this to figure out a percent mass dry trimyristin. We need that percent dry mass to know how much trimyristin we extracted from the nutmeg, and to calculate how much trimyristin we used in part 2. So those should be 2 different things, right? Because this is all of your trimyristin. This is what trimyristin was left after you set aside some trimyristin. Okay, so these are 2 different values. Does everybody see that? Okay. The other thing you're going to want to do once you have this number is you want to figure out the weight loss on drying. Okay? So if you know your weight of trimyristin, wet and solid, then you can figure out what percentage of it is the trimyristin, okay? And if you take your total original weight minus that weight of trimyristin, you can figure out the weight loss on drying. Does everyone understand that? So the weight that you lose is lost to solvent, so that's the weight that was lost on drying. That sound okay? Okay, so that's another calculation you're going to need to make, okay? So we're going to look at now what we're going to do in part 2, okay? So part 2, we're going to use what's called a saponification reaction. And so remember, the saponification of an ester, remember trimyristin is a triester, okay? And so this is a reaction that soaps are made from. Okay? And this comes from, although a lot of soaps aren't necessarily made from naturally occurring fats anymore, but it's the basic hydrolysis where this name comes from, is the basic hydrolysis of naturally occurring fats, and hence that's how you would form soap, and so that's why saponification and soap sound very similar to each other. And so what you get from this is the sodium salt. In general, when you do this base hydrolysis, the sodium salt of the fatty acid, that is the soap. And so it's a way to solubilize non-polar compounds that wouldn't be soluble in soap alone, or sorry, in water alone. So what happens, and this happens when you get to biochemistry, you'll talk a lot about this in terms of lipids, but this is also how soaps work. So we've got this long chain of carbon and hydrogen, and then when we make the sodium salt of the triester, so if we saponify our, sorry, trimyristin disappeared, but if we saponified our trimyristin, this is what we're going to get, this sodium salt, okay? So you've got this long nonpolar chain and then a little bit of charge here on the end. So how this works is, say you've got some dirt here. That long chain goes around the dirt, but then the polar end, the charged end, sticks out in the water. And so this is how you get rid of dirt. This is how soaps work for removing the dirt, because dirt is usually non-polar, not polar, okay? So this is called a micelle, is what forms. And like I said, in biochemistry, we'll talk about this even more so, okay? Now for what we're going to do, we need to look at the reaction itself. So we've got our trimyristin here. Draw that guy again so we can fit everything on here. You're going to take the solid trimyristin that you extracted from the nutmeg. And remember, again, you want a gram of trimyristin going into this reaction, otherwise talk to your lab prof. So here's our trimyristin, okay? Real key with all of this is remembering stoichiometry. Okay, remember this is a triester. There's 3 esters for each trimyristin. So that's going to be important for figuring out what you have and how much of things you have. Okay, so here's our trimyristin. We are going to react it with the base we're going to use is sodium hydroxide, because there are 3 esters. We need 3 equivalents of sodium hydroxide. Okay, so we use the same 2 molar sodium hydroxide that you did in experiment 1, but we need 3 equivalents of sodium hydroxide. This reaction we're going to carry out under reflux, and we'll talk about here in a minute what that means. And we're going to use ethanol as a solvent as well. We've got water from our base, carrying out at reflux, okay? So we're going to add heat to this reaction. We're going to form glycerol. So remember, trimyristin is the homotriester of glycerol. We're actually going to make our glycerol. Okay, so here's our glycerol. And then we're going to make our fatty acid, our sodium salt here. So our soap here. So you'll have 3 of these guys now. So here's our sodium salt, and this is called sodium myristate. water soluble. And this is a soap. It's going to act like soap. You'll see it kind of look bubbly, like you've got a soap solution in the ethanol and the water, okay? So then we're going to take our 3 equivalents of our soap. We want to get it out of the water, okay? We don't want it water soluble because then there's no way for us to get it out. So what we've got to do is just like we did in experiment 1 when we had the sodium salt, we'll go back and protonate it again. So again, we need 3 equivalents of HCl. And then you will form your myristic acid. Okay. And so you should see a difference here between its basic form and its acidic form. It's not water soluble at this point, okay? So it's going to precipitate out at this point. And we also get sodium chloride that's formed in the mix, okay? So we're going to filter this, all right? And then we will recrystallize it. And then you will analyze it. Okay, we have to, once we've started this process, you have to this week get to the point that you filter. You have to filter the myristic acid off, okay? Don't leave it in the HCl. Don't leave it basic. Protonate it with the HCl and then make sure you filter it. You have to get to the point that you filtered that solid, okay? Otherwise, this mucky slime forms and it's really hard to then collect later, okay? So make sure you get to the filtration here, that you have that solid myristic acid. If you have time, then go on and do the recrystallization as well, all the better, okay? Otherwise, this recrystallization, you could do an open lab. Just make sure that your lab prof knows when you're doing it and you've arranged a time that they're available to know that you're in the lab. And you have to have a buddy with you, okay? So it's not like melting points where you can go in on your own. If you're going to do the recrystallization, you have to let your lab prof know. You have to have a buddy with you that is dressed properly for lab, whether it's another organic lab student or not. But they have to go into open lab with you, okay? The other option is if you feel like you work at a pretty good pace, you could wait to recrystallize next week during after you finish experiment 4 because it probably won't take the entire lab period. But think about how you work in lab, okay? If you'll have enough time to do both of those things next week or if you need to get the recrystallization done ahead of time, all right? Make sure for this recrystallization, follow the directions very carefully, okay? It's a tricky recrystallization, so make sure you follow the directions. If you follow the directions, you'll be good, okay? If you're not clear of the directions, make sure you ask before you start. Because once you've started, if things aren't done correctly, it's hard to get your stuff out, okay? All right, so in lecture, next semester, you'll look at esters, okay? And so first of all, here's Flowchart from the Prelab. I've gone through, we talked about the extraction of the trimyristin. Then this was, we did the reaction to form the myristic acid, and then the workup was working it up with HCl. You filter off all of your impurities, including your glycerol. You've got your myristic acid, and then you recrystallize to get your pure myristic acid. In your textbook, either the 6th edition, it's page 792, 7th edition is page 810, there's a general mechanism for base-induced ester hydrolysis that you'll go through next semester, okay? And so that's basically what we've done here is basic hydrolysis. So you have attack of the OH group on your carbonyl carbon, you form a tetrahedral intermediate, you lose your OR minus, and then you deprotonate, and then you need acid to reprotonate to get the carboxylic acid out. Okay, so if you want to read more about this, it's in your textbook, and like I said, you'll cover this next semester. Okay. Now, the key new equipment piece to this whole thing is the reflux apparatus. Okay, so when you're doing the hydrolysis reaction, we're doing this at what is called reflux. Okay, and this is the apparatus that we're going to use. For reflux, we're looking at the boiling and condensing of solvent, okay? And so I'll tell you why we do that. But you need both. You need boiling and condensing of solvent to keep reaction at a constant temperature. So the boiling point of a particular mixture is characteristic of that mixture, okay? And it doesn't matter how much heat you add to the system. Once you get it boiling, it's not going to go above that boiling point unless it doesn't have any solvent left, okay? And so that's why we are boiling or refluxing, is to keep your reaction at a constant temperature, okay? But to do that, we also have to condense the solvent so that we don't end up evaporating all the solvent and then basically charring your reaction, okay? So it's the boiling and the condensing of that solvent to keep it at a constant temperature. And so this is used, reflux is used all the time in organic chemistry as a method of heating something, because it's, once you get to the boiling point of that solvent, it's really easy to control the temperature of that reaction. So you're going to be setting up a reflux apparatus this week. You're going to use your heating mantle for the first time, okay? And check with your lab prof, but I would recommend probably putting it on your stir hot plate so you can actually stir your mixture. Or you can set it up like this, but then you need to use boiling stones in here instead of a stir bar, okay? You're going to have your heating mantle that, remember, is connected to the ohmite. Remember that special plug on your hood with the switch. That's where the heating mantle goes. It does not go in the regular wall outlet that's on your hood, okay? So be really careful that it goes in the right spot. If you put it in the wall outlet, it's going to heat really fast and get your reaction way too hot, okay? So make sure you put it in the right place. So you'll get everything set up, and then have your lab prof check it, and then when you're ready to go, you'll plug in your ohmite into the, or you plug in your heating mantle into the ohmite, turn the switch on, and control the heat with the dial instead of it going into the wall, okay? You're going to clamp your reaction flask really well. Then you're going to put your Liebig condenser on top. You want a clamp here that's loose, so you can raise your flask up and down once it's done heating. And you're going to have water in your condenser to keep your solvent condensing, okay? So water in on bottom, water out on top, so that you're fighting gravity and fill your condenser, okay? You do not start your reflux time until you actually start refluxing, okay? So when you start seeing boiling and condensing, that is when the temperature, when the reflux time is started, okay? And you have to do this for 45 minutes this week, okay? So don't start counting your time when you plug everything in. That's not when it's refluxing. It's refluxing when it's actually boiling and condensing, and your 45 minutes starts then, okay? Then, so what I would do is work to get to this reflux, okay? Then when you get to this reflux, you can worry about things like dishes and things like that, okay? So don't spend a lot of time up until this point cleaning things and getting things in order until you get to the reflux and have some time to worry about stuff. The other thing is, once you get it refluxing, you need to keep an eye on it, because sometimes it'll take a little bit of heat to get things boiling, and then it doesn't take as much heat, so then you need to adjust the heating mantle afterwards too. So keep an eye on this one, okay? Okay, a couple more things real quick before we go that you're going to need to know for your identification, okay? So you are going to have two things that you need to look at for this experiment. You've got a whole lot of calculations that I went through and then you have two products that you need to identify and characterize, okay? You have your trimeristin, and you'll have your myristic acid. So using something that we've used so far for characterization, how should we characterize these guys? We can use melting points, right, to characterize these guys. For this one, what are you going to take the melting point of? The trimeristin. What will you have left?
0.1 to 0.2.
Right, so that little sample that you set aside, you set it aside to get a mass to see how much it weighs after it's dried, but you also will use it to get the melting point of your trimeristin. Okay, so after you've weighed it, don't throw it away, because this is how you're going to get the melting point of your trimeristin. Okay, then you'll have your solid myristic acid after you recrystallize and it dries. Okay. You do not have a standard for trimeristin or a standard for myristic acid. And if you look in at that Prelab, they have very similar melting points. Okay. So how will you know that they're different? So if you look at myristic acid, its melting point is 54, trimeristin's is 56. So they're really close together. So what could you do to figure out if they're the same thing or a different thing? Mixed melting point of the two, right? But it's gonna, you want the opposite effect of what you were doing for experiment 1, right? Because you want to see that they're different. Okay, so you want to see depression and broadening of that melting point, okay, of the mixed melting point. So you need melting point, mixed melting point, okay? And just like experiment 1, you'll probably want to do, if you want to, you could do a fast one or a slow one, or they're low enough melting, you could just set it to do the slow one, okay? All right? Then make sure you take care of, you need your yield of your myristic acid, and then you also need all those calculations that you have for the trimeristin, okay? So don't forget that. All right. Any questions? Okay. Good luck. Just make sure you're really prepared.